So in the previous homework we looked at relative minima, relative maxima, we looked at how to find critical points, we went over the extreme value theorem, and in this next homework assignment you're going to apply those principles to solve application problems. So I'm going to work through an example, and as I do I'm going to try to talk about some of the things that we need to take into consideration when we're working on these types of problems. So this one says a rectangular box is resting with its base in the XY plane, so that's right here, with one vertex at the origin right here, and the opposite vertex in the plane 6x plus 4y plus 3z equals 24. So we have the vertex opposite the one set at the origins up here. Find the maximum volume of such a box. Well, this really typifies, I think, extrema problems when we're working with functions of two variables. The idea is you always want to be able to come up with a function for the thing that you want to minimize or maximize, and then you typically need a constraint function. And if you can come up with a domain, especially a bounded domain, then that's a good piece of good tool to have in your pocket. So in this case we've got a box, and just thinking through the box for a minute, base in the XY plane, so it's going to be in this direction it's going to have a width of y, in this direction it'll have a width of x, and the height on this is going to be z. So if we're trying to maximize volume, we need a function for volume, and our volume function is just going to be x times y times z. And then what we want to recognize is that this plane, we know how to represent a plane by finding the intercepts and then drawing it in. So the plane's actually been drawn in here, and what we're doing is constraining this box in octant 1. That's the constraint. So the plane is, this is the function we're trying to maximize, and then we have the constraint function. The plane is the constraint function, and it's actually going to give us a box that lives in octant 1 and is bounded by the xz plane, the yz plane, and the xy plane. So if we think about the domain for our volume function, the domain is going to be this region in the xy plane that is constraining the box in octant 1. So we're really, in terms of thinking about a domain, which is just going to be a region R, it's going to be the line x equals 0, which is the y-axis. It's going to be the line y equals 0, which is the x-axis. And then we're going to be bounded inside of this line as well. So the region is going to live in here in the xy plane. And this line right here is, if we think about the line in the xy plane, it's going to be, this is at 6, 4, so it's down 6 and over 4. So negative 6/4 is the slope, times x plus the y-intercept is 6, and then this could be reduced to negative 3/2. So this is our domain. So we have a closed bounded region inside of which the box needs to live. And what we want to think about is, if we're on, remember, extreme values can occur either at critical points on the function, or they can occur on the boundary of the domain, on the bounded region that you have for your domain. So in this case what I want to think about is, can the maximum box volume occur on the boundary? And the idea is that it can't, because if we're on this line right here, x is going to be 0, which would give us a volume of 0. If we're on the line right here, y is equal to 0, so we would have a volume of 0. And anywhere we move along this line, z is going to be equal to 0. So the volume will be 0. So the idea is, on the bounded region over which you're constructing your box, on the boundaries of that domain or region, the box volume is going to be 0, and that's going to be a minimum. So what that tells us that is, if we can find a single critical point for a volume function, that critical point is going to correspond to a maximum. So when we do these extrema problems, we want to make sure that we can make an argument or a case that the thing that we're finding is a max or a min. And the ways that we can do it, we can do an argument like I just did here, where I identify that anywhere on the boundary of the region that I have a volume of 0, which will be a minimum. which means if I find a single critical point, it's going to be the maximum. That would be one way to make an argument that the thing I was finding was a max or a min. We might be working with a surface that we recognize as a quadric surface. Maybe we have a paraboloid opening upwards. So we know when we find the critical point, it's going to be a global minimum. We may have a paraboloid, for example, opening downwards, and we know when we find the critical point that it's a maximum. But when you're doing homework problems, you want to make sure that you say that. If you know it's a max or min for that reason, say it. It's important to say it on exams to get full credit. The other thing that you can do is run the second partials test that we looked at in the second homework. And the second partials test might identify to you that you have a relative maximum or a relative minimum. And then you make an argument that based on the domain of the function, the working domain of the function, that relative maximum must be the maximum you're looking for, as an example. So let's go ahead and knock this particular problem out. So the idea is we want to find the box with maximum volume. So I know how to find the volume of a box. And then what I want to do is utilize the constraint function. So we want to solve the constraint function for z. So if we do that, we'll get z equals, it'll be 24 minus 6x minus 4y. And then we would have to divide by 3 to isolate the z, and then we'll put 3 into each of these coefficients. So where's my eraser? There we go. 3 will go into the 24, we'll get 8. 3 will go into 6, and we'll get 2. And 3 going into 4 will just be a 4/3. And the idea is then I can take the constraint function and substitute that constraint function in for z here. And I wind up, instead of knowing the volume as a function of 3 variables, now I know the volume as a function of 2 variables, x and y. So we get x, y times, and it's going to be 8 minus twice x minus 4y over 3. And I'm going to go ahead and distribute the xy into the parentheses. So 8xy minus 2x squared y minus 4/3 xy squared. And my reason for doing that distribution is, for me, I think it's going to make taking partial derivatives a little bit easier. So the idea now is we know that the maximum isn't going to occur on the boundary of our domain. So we're going to look for critical points, and critical points are either going to be those places where the partial derivatives are undefined or don't exist, or where the partial derivatives are simultaneously equal to 0. And in this case, we're going to get partial derivatives that are always defined, so we're going to need to find when the partials are simultaneously 0. So looking at my volume function, first I'm going to calculate the partial derivative with respect to x. So just walking through here, I'm going to get 8y, and then here I'll get minus 4xy, and right here we're going to get minus 4/3 of a y squared. And then notice that a 4y is a common factor in all 3 terms, and I can factor that 4y out, which would leave me 2 minus x minus 1/3 of a y. The partial derivative with respect to y is also needed, so we'll come back up to our function right here. So with respect to y, we're going to get 8x minus 2x squared, and then minus 8/3 xy. And then I want to notice that a 2x shows up in all of the terms, so I'm going to get 2x times, we'll get a 4 here, minus an x here, minus a 4/3 y right here. And the factored form is going to be nice because we know that we need to set those partials equal to 0 to find critical points. So we need to set the 4y times 2 minus x minus 1/3 y equal to 0. And the zero product property says that either this needs to be 0 or this needs to be 0. So y equal to 0 would correspond to an important value, except we know that the volume of the box will be 0 if y is 0. So we don't need that. but we do need to set 2 minus x minus 1/3 y equal to 0. And then I can probably multiply through by a 3 here just to clear the fractions a little bit. So 6 minus 3x minus y needs to equal 0. And then the same thing here. I've got my partial derivative with respect to y, which we also need to set equal to 0. And this will equal 0 when x is equal to 0. But we know that x equal to 0 corresponds to a volume of 0, so that's not going to be the maximum volume. So we'll take the other factor and set it equal to 0. So 4 minus x minus 4/3 of y needs to equal 0. And then if we multiply through by that 3, 4/3, we would get 12 minus 3x minus 4y equal to 0. And so we need these two equations to be simultaneously 0. Here I've got the 12 minus 3x minus 4y equal to 0. And we've got a system of two equations and two unknowns. So we just need to solve it for one of the unknowns. And what I want to notice is if I subtract this equation minus this equation, the x's will zero out for me very easily. This is a minus 4y. So I'm going to get 6 minus 12 is minus 6. Minus 3x minus 3x will be 0. Minus y minus 4y will be plus 3y. And that will need to equal 0. And then when I solve this for y, I get y equals 2. And then we can back substitute that into one of the equations. So here I have 6 minus 3x minus y equals 0, so minus 2 equals 0. And then that's going to give us 4 equals 3x, or 4/3 equals x. So we have a critical point at 4/3 comma 2. And we know that that's going to correspond to a maximum for the reason I explained earlier. We get 0 on the boundary. We have only one critical point showing up. We know that the box lives inside of this prism right here. This prism has a finite volume. The box has a finite volume. So we know the critical point is going to correspond to a maximum volume. If I didn't know that, I could apply the second partials test that we looked at and verify that I indeed have a maximum. And then it says to find the maximum volume of the box. So really all I need to do at that point is go to my function of two variables right here and plug in my values for x and y. So v of 4/3 2, and you just plug stuff in and then simplify. So 4/3 times 2 parentheses 8 minus 2 times the 4/3 minus 4/3 times the y, and then we simplify this. So you know how to simplify as well as I do, so dot 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 right there.